Thank you all for coming out. My name is Gabriel Orant. I am the Accelerator Director here at Startup VC. Most of you are like, what's Startup VC? So Startup is a venture capital firm here in New York, and I run the Startup Accelerator wing of that firm. And basically, we use the accelerator as a pipeline for deals. So what does Startup do in terms of like, what's our MO? Who do we take as startups? We focus on international founders like Sergey that are trying to break into the US market, usually with traction in their home markets. And the whole idea is we'd like to find, foster, and fund these startups. So we don't invest in all of them. We do with our programs and services, but at the end of the program, we do make investments in some of the companies. So it is a 3-month program here, right here in New York, in this very room. We have a co-working space there. And so we work with all aspects of the business. So from communications, to product, to sales, to marketing, SEO, digital marketing, fundraising. We even have an acting improv workshop that our founders do to kind of get them loose, get them out of the ropes, out of their skin. I'm going to let these guys introduce themselves, but I wanted to let you know what we do here at Startup. And if you have any questions, feel free to come up to me afterwards. But I'll let you guys begin. Here you go.
When we start, so my name is Sergey. I'm founder of SmartyKit, a company that does computer kit that you can use to build your own #1 computer. And so this is tech. This is a thing that can bring technology to the modern generation. Connect like the guys who did in Silicon Valley back in the 70s, and the kids of the Generation Z, they use TikTok every day and follow our online instructions. And cool thing that the processor that was used in #1, it's actually a processor that was really good and is used until now in many applications. And Bill Mensch is the man who was part of the original 6502 team, and now he has his design company here in the US, and they design and produce 6502 and many other processors and controllers. And for sure, he's a guru of chip making in the US and in general in electronics. And it's a big honor for us that Bill is our advisor and investor. Thank you for this, Bill. And for sure, Bill is engineer and he knows a lot about chip making, about electronics. And so today we're going to talk about this, and I hope that you all going to learn more about what is inside all these electronic devices that are all around us. And also, Bill has some materials to show, and it's really nice because I'm also excited because my background is an engineering one, and I like all these things, and hopefully you're gonna like it. And also, yeah, I can show that this is the kit that we produce right now. It's assembled in Paris, France, and also you can see the demo boards right there, so you can really check what we're doing. And also there is a single board version of it, so it's like everything you redesigned. And the cool thing that we approach this using TikTok, and in just one night we got almost 200,000 views in just one night. Yeah. So yeah, we just shot the video about this board, the design, and we said it's something like everything started in the garage, and like many people started to ask questions, like 2,000 likes. It feels like it's huge, and some of them were asking what specifically used, and I was very interested about it, and that was really fun. So hope that we can do more materials for this new generation and we can simplify this entrance to the world of technology. And thank you guys for coming. I hope that you would enjoy this thing, and for sure questions are more than welcome, because yeah, the main idea of this event is to share this knowledge this generations of engineers, and all the guys want to learn more about how this computing evolved for the future to another technology where computers and smart devices are around us, and all these other intelligence and machine learning stuff is for sure the new way of building some to help you take the life. So thank you. It's all good. And yeah, so I'll do this and another thing to do. Probably you can tell more about your life and how you became this engineer.
Hello, it's good to be here tonight. Good to see you. First of all, I wanted to say for decades, I don't know how many decades, 3, maybe 4, I've been looking for the next Boston. I think I found it. So, yeah, you're welcome. But anyhow, I've been designing microprocessors for 51 years now. I'm still working, designing. I have no plans to retire. Although I do live on ASU, Arizona State University's campus in a retirement community on campus. It's a new style community. So although it's a retirement community, I'm not really retired. So, but anyhow, I really enjoyed that, that Sergey created this SmartyKit. It's really awesome because it engages next kids or adults that have never experienced that type of a computer before, like the Apple I. So Sergey's computer right now gets you involved with it by plugging things in. That's like Montessori. If you know Montessori education, it's about the more senses you involve, the more you learn. So when you plug things into the breadboards, you can remember things better because you're using your touch sense. And so I really like what Sergey is doing here. So I got started as an engineer at Motorola in Phoenix in 1971. That was 6 months later is when Intel announced their first, which was a microprocessor for calculators, which is kind of a weak microprocessor actually, but it's still a microprocessor. So what happens is I was part of the engineering design team that created Motorola's first microprocessors. Then they wanted to move me and some of the other engineers to Texas, and we didn't really want to go to Texas. So we went to Valley Forge, Pennsylvania, to work at a company called MOS Technology. That's where we created the NMOS version of the 6502. Then after MOS was acquired by Commodore, then I saw the focus being on game systems and low-cost computing systems that had some unique features in it. And I like general purpose. So all of my chips are general purpose chips. So I really like it when I meet somebody that's using my chips because we can celebrate together. So anyhow, it's that aspect of what I do that I really enjoy because I really enjoy people that use my technology for their own successes. And Wozniak and Jobs getting started with the 6502 was a big deal. Atari and Commodore and Nintendo, they used my technology. Also, I brought a pacemaker here. So there was about 6 companies I licensed on my microprocessors for life support. And I did that because nobody else wanted to have their technology, their microprocessors used in life support because they were afraid of getting sued. So I solved that problem by being indemnified by those companies I licensed for. So I've never had a problem. All the pacemakers work good. So it's that kind of application of my technology that really keeps me going. It's something that I really enjoy, so that's why I want to continue doing this. And that's why I love supplying chips to Sergey for his little computer, and that's going to change the world. So that next generation will be able to work with the technology in the forms that Sergey comes up with. So along those lines, I'm also right now recreating a class that teaches silicon systems on chip. That's SoC design and tape out. You can actually tape out a chip. of your own. If you work with a professor at a university, you can tape out a version of yours as chip form, right? If you wanted to. But I love the format you have it in right now. So in other words, so we want to teach how to use the microprocessor system on a chip, which is lower cost, lower power, easier to use. You design it for the functions that you want on it. So that's part of this. And so in order to get the next generations of engineers to be think about it, we need SmartyKits. We need people that can actually feel good about it and feel successful in doing things. Maybe writing some code for it, adding some features to it, whatever I think your tutorials might have that will help people get started. So that's kind of how I relate to what Sergey is doing here with the SmartyKit, and also that supports new engineers that want to work with my microprocessor. That's got to be good. That's good. So I wanted to show you some things, and then I don't know if we have questions then, but this is 100 6502s on thin film. Okay, and I'm going to show you this. This was manufactured in Cambridge, England. So this is an 800 millimeter wafer. It's glass. So it's actually glass. It's not silicon. Well, it might be silicon because it's glass. That's how it's manufactured. And then so how they manufacture only glass, and then what they do is then they can peel it off. So these are all 65 CO2s. The same function that was in the Apple IIe, same function that's on Sergey's board. So these are the same ones. These are meant for putting labels on things. So they want to build trillions of these for everything that has a label. This is RFID, so you can read the code off of this. So each thing that you buy will have a unique ID on it. So that's how that's meant to be. So this is system on labels. So they asked me, we're partners with this company in England for creating these systems on labels. So it's just another thing. You want to be able to have that same technology that I was just talking about with system on a chip, with the system on a label. So if you visit my websites, I have cards for each of you if you want a card of mine, then you can see the websites that we have. So there you have it. I got other goodies up here, but I don't want to steal the spotlight from the SmartyKit.
I have some questions.
Yes.
Yeah, so I have a question. Yeah, like when we imagine like 70s, the beginning of this computing era, like we have like this Intel 4004 is just coming in, and as I understand this, the general idea of CPUs in general was like before this, in order to change something in a simple thing like calculator, you need to redo all this hardware. And so the guys decided maybe we can create some universal device like a processor that we can produce in very, very big batches to save money. And then we can change the behavior of the system, just changing the code, which is much simpler. But then how, just like what kind of people just like were involved in all this? Maybe you can tell more about this, what kind of engineers, how did they came up with this idea? And so just how it was everything like in the beginning. So because it's really interesting.
Yeah, so actually, we all stand on the shoulders of giants, right? So IBM created computers, obviously know that. But the IBM 360 was an interesting computer. It was the first integrated circuit computer that was scalable. In other words, you could build small computers like, they didn't call them mini computers, but they were small computers like a mini computer all the way to the largest mainframes. That was actually an 8-bit microprocessor that they did that with. And so what's interesting about that, they chose instruction set for that. So you have these engineers, this was from about 1965. I was at Temple University at the time. That's when they introduced the IBM 360. So then you know about mini computers, you know about the Digital Equipment Corporation, maybe the PDP-8, PDP-11. Well, the PDP-8 was used as a model for the Motorola 6800. So the PDP-11, which was far more powerful, was the model for the 6502. So if you looked at the programming card of the PDP-11, you'll see the same 3 characters for the instructions. So it's kind of one of those things that did we come up with a whole new instruction set? We did it. We looked at what other was successful, and then we want to repeat successful ideas. So that's what we've done. And so there's another microprocessor that came out before the 6800 at Motorola. While Intel was working with Japanese companies, calculator companies, that's where the 4004 came from. Motorola, being the second largest semiconductor company in the world at the time when I worked for them, they had been working with companies in Europe. So Precisa was a calculator company. We designed, at Motorola, I didn't design, but the team that I joined designed far more powerful microprocessors for calculator chips before Intel, but Motorola was not as good at marketing as Intel was. so therefore you hear about Intel as the first one. But anyhow, so going back to that, there's a company, one of the most powerful companies, I think maybe still in Italy, was Olivetti. So Olivetti came to Motorola, and actually I was one of the 2 design engineers that completed the Olivetti desktop CPU. And actually the first pictures of the 6800 were actually pictures of the Olivetti CPU. It was an 8-bit CPU. I was one of the 2 engineers that completed that project. And so that has some of the features of what you could say the 6800 had and the 6502 had. So it's not like, the 6502 was just right out of the, just hit a home run, right? We did hit a home run, but it was after we had a few on bases. So for me, I knew that this technology was going to change the world. We knew that. And Rod Orgel and I, we were the 2 real semiconductor engineers that put that together. I was the lead semiconductor engineer on 6502. And I also designed the PIA that was used on the Apple I. So the Apple I that made that possible was I had a socket on there for the 6502, and then he had the 6820, which is the PIA, which I also designed. So I designed a lot of chips for microprocessors. Our most popular chip is a 6522 PIA, and that was the next generation of the PIA that Wozniak used. Well, little known fact is that 6522 is our most popular chip today, used with basically all the microprocessors at one time or another. But the other thing that it was the original interface for the mouse for the original Macintosh. So that 22 is, I had chips in both the Macintosh and the Apple II. It's kind of fun. So anyhow, it is that background of systems on a chip or individual like IO interfaces and a microprocessor that keeps me interested in all kinds of things. And the 6502 is probably the broadest use cases of any microprocessor of all time. Like Intel has never designed a microprocessor that keeps people alive, life support. And so I'm saying is we have from life support to SmartyKit. So I'm excited about it, and I think you can see why I would keep doing these things, because I just happen to be in a good spot. And if someone says, how do you, whatever, how do you do this and how do you stay in front of that? It's like, you ever play crack the whip on ice or something like that? Where the one in the front doesn't have to go so fast and don't go so far, the one on the end of the line, they have to go a lot further. And so it's easier for me just to stay here. So when a company like this one, and this is Pragmatic is the name of the company, and Pragmatic came to me and said they'd like to build a smart label out of my chip. The same technology used in here also is in here, which this little black chip is built by Intel. So I don't know that Intel knows that a 6502 is in their chips, but there is a 6502. So these are modules that you can hook up to this. These are I2C. This is SPI. This is a GPS. This is a Wi-Fi and Bluetooth, and so you can hook up about 1,000 different things to this structure. So there you have it. But back in the day, there was just a few engineers at Motorola, and Rod and I were 2 of the 4 engineers that are on the patent. So it was a small team. If you want to see the team and you want to see some of the background information of the original 6502, you go to team6502.org. Jennifer Troutwin, Winograd, she was Terry Holt's daughter. She was 6 years old when we designed the 6502. She put that website together, and she also is the voiceover in the 5-minute video, which is really, she's done a great job on. So I like promoting it. She promoted it, or she created the website so that the rest of the team could be recognized. And her dad was the real reason why she wanted to do it. Her dad passed away last September, I think, a year ago. But anyhow, if you wanted to find out more, there's a ton of stuff on it. It's the most documented microprocessor of all time. So there's plenty of information. You can go wear yourself out trying to find it all. Okay, do you have some more questions?
Yeah, sure. Yeah, so like engineering team wasn't, as you say, it wasn't really big, like for engineers, for the chip. Yeah. And the question is like right now we have a lot of software like to do this stuff. Like we have all these post-it notes like Miro, boards, I don't know, Jira, and all this wonderful stuff that help engineers to do the work, to track the tasks and to collaborate. And what did you use at that time in order to like day-to-day basis in order to make this project? What kind of like organization it was like? How did you collaborate with the colleagues, and to have some kind of a battle plan on somewhere in the wall where just like track the progress? Just it's really interesting how everything was organized in the engineering team.
So your question is, how do we manage all this?
Yeah.
Okay. Well, actually, we were a very close team, so we didn't really have many meetings. We didn't. We just knew what we needed to do. We stayed in our own lanes. The mass designers, that would be the little designers of the actual chip layers. My wife over here, Diane, is a mass designer. She's been working for 42 years with me. And so she's actually created the system on chip design. I taught at ASU for 5 years, but she actually did the design, mass design. So when we did the mass design, we did it on Mylar. Mylar is like plastic paper, so that you would write on that with plastic pen or plastic ink. And so you could erase that. And the reason why it was used on Mylar is because Mylar didn't expand or shrink down based upon temperature or humidity. And so each of the corners of every shade had to be digitized. So that's how we did everything. We did it with pencils and paper. And then we put them together like paper dolls. If you ever worked with paper dolls, it's kind of how we did these things. And we took pieces of the chip, like for instance, the X register was 8 cells. Most of those cells are the same. So you could say that the first cell might be a little different, but you wanted to keep them the same. So in other words, you used each of these types of circuits, like for the adder, that was a complex circuit, but that was a complex cell. And so each of the different registers, like the program counter is a 16-bit register. And so we had to look at the timing for carrying 16-bit increment for the 16-bit address bus. So you actually had to work at each of the cells. And then also in order to get the performance, which the 6502 was the highest speed chip of its day, we had to look ahead carries, we did other things. So we really took the time to really make sure we did everything the best we could. And that's one of the reasons why 6502 is still popular. It's still very usable in a lot of use cases, and we're going to have a lot more when we get these classes done. But when you look at the 6502 and what we did back then, we took the time to do it right. And so we really are proud of that design. And I call it a timeless architecture. What do I mean by a timeless architecture? That means that nobody can do a better one. That means forever. So if you want to try your hand at it, you can try, but you're not going to beat it. And that's where, when I found out GTE was one of my early licensees of my 16-bit processor, when they did benchmarks against the 68,000, the 6800 was easy to beat, but then the 8086, we have these benchmarks online, we can see what they are. But we were either 2 to 4 times faster at the same clock rate. And so that's because we took the time to do it right. And when I found out we were so much better, GT says, do you know you beat their benchmarks? I go, oh, we do? Oh, really? And then they showed me the numbers. I go, oh, that means that Intel overall didn't do the best they could have. That's all. But we did.
Regarding the timeless design, once it was a quote from Tarantino, he was asked to like, why couldn't you shoot something better than Pulp Fiction? And he said, well, like, why cannot you make something better than Pulp Fiction? And I say, I cannot, but who can? So it's like the same the timeless design. And also the question is, like, as I got, you have the team of engineers, but maybe you have some manager who just like, guys, you gotta do it. No, somebody from the management will try to like, to speed you up or do something like with trying to get some incentives for you to move on, or just like we're like more like self-organized team that just like really know what to do and they just okay, like you got what you're doing and saying that you're professionals and just wait what it was.
Yeah, we didn't need any encouragement. We didn't need anybody to tell us what to do. We knew what we wanted to do. And so it was a great team. And you'll see that if you visit that team6502.org, you'll see that we were just a great team. It was a small team. And we knew, Rod and I knew we were going to change the world. We knew that. Now we're changing it again.
That's
Right?
good. I mean, I think it's just it's also the timeless team design. I mean, if you just like know your stuff and if the management doesn't involve in this, like just saying stupid things like, hey, let's move on, we have a deadline. Yeah, I have a call with the big boss on this Friday. You just like, yeah, that's really good that it was like this and that. That's how we can probably do really something great, like that can change the world. That's good. The next question is, what do you think about this trends right now in this chip design and like, because everybody's trying also, to split like it's not just a CPU, it's also GPUs, it also like stuff like Apple does in their like, I mean, that they do it like part of their CPU, but I mean, it's different zones for these they call bionic and all these things were like where all this industry is moving right now and like what are many challenges regarding the exponential growth of machine learning tasks and artificial intelligence. Please tell more about this.
Sure. First of all, I don't like when they use the term artificial intelligence. Artificial, one of the definitions of that word is false. There's no false intelligence unless it's a human. And the human is the one that's got the artificial intelligence because they're fed bogus information and they don't know it. So that's false intelligence. That's AI. But when I look at what's going on in the world, it's really machines, and it's really humans are teaching machines. The machines are learning, or is it really? So we have USB ports on these machines that we can actually teach the machine. And so we don't have ports, we don't have USB ports on humans yet. But anyhow, I think we will. I hope we don't. But anyhow, but the GPUs and these other functions that would give you more power to run through code. So like right now, my smartphone that I probably have here someplace here, this one here has like 4 processors running in parallel at 1.2 gigahertz, and it's got 256 gigabytes of flash memory in it. I don't forget, I think it has, no, that's my PC, it has 32 gigabytes of SRAM. So once you get there, that is less interesting to me. I mean, what you've got is more interesting to me. These little systems are more interesting to me. And actually, this chip here, this has, it's got a processor and it has, I think, 4 VIAs in it, and has 4 ACIAs in it. It's got the interface for I2C, SPI, all of that in there. I did a little work on it, but it's not the type of work I like doing. I like doing the work that Diane would do. So in other words, the schematics, it's the real thing. This is all hardware description language. Verilog HDL is what it is. So when you go to HDL, that's what we can do, and that's what we're actually teaching. But we also want to teach the world how we design the chips in the first place. And that's what I love doing. But it's now, by the way, there was an archaeology magazine. It was July, August issue about 8 or 10 years ago. There's if you visit Visual 6502, there's a couple of artists, or I'm not sure whether they're artists or what they're, but a couple of guys out of Canada took the layers off of the original NMOS 6502, and they you can watch it run. You can watch it actually run. If you put some code in it, watch it run online. And so this guy from Archaeology magazine, a journalist, calls me one day and calls me and says, "Do you know what's going on with these guys with Visual 6502?" I said, "Yeah, they called me a couple months ago. They were having problems trying to figure out, I think it was set overflow pin. They didn't, I don't know what they were asking me at the time, but they said, so you know about them?" I go, yeah. In fact, I said, since you're in archaeology, I said, you might want to think about this. I'm still here. So it's like if you are digging in some pyramid someplace and there's a mummy over in the corner, goes, look over here, there's something interesting. That didn't make his article, but you can read the article, which is fascinating. So that's part of why I want to have this class of the actual, how we design it. So your questions are very important. I think it's very good that you're asking these questions because it's a lost art. And when you go to the RTL for these GPUs and these other things, it's got, number of transistors on it. I mean, it's like use a bigger hammer, right? Well, for some, that's awesome. It takes hundreds of engineers to do it. I like doing things where my wife and I can design the chip.
Thank you, Bill. And also, there's a question like we have a lot of students today, and probably you know about Sanzello, who does the chips at home. he actually, yeah, that was fun. But right now, what I've seen is like he's doing very simple things. It's just few gates, right, on the chip. But like hypothetically, how long would it take for a person, for example, trying to build like a kind of processor like 6502 just at home? Is it possible or is it not possible? I mean, if you just like have like all the resources you can do, like bring the silicon, trying to do this, is it possible? Could you please tell more to the guys about the technology? What is like crucial components in order to be able to make chips like this?
Okay, well, passion to do something. You know what I'm talking about. So what I'm saying here is that I would never say that doing something at home, first, there's chemistry involved with this, and some of those chemicals aren't really helpful for the human body. And Steve Jobs, passed away a few years ago from pancreatic cancer. And there were several of the people that I've worked with years ago that were making PCBs in their labs. And they all passed away from pancreatic cancer. So I have to be careful about the chemistry. Now, if they're using things like chemistry from oranges or citrus, some people are doing things with citrus for PCB, and that's not dangerous to the human. But a lot of this is carcinogenic kinds of materials, so I'd be concerned about that. I don't know what they're doing. I don't know what he's doing. But to actually design a microprocessor, let's say he wants to design a 6502, then I would say, could he do it? Yeah, possibly. Not unlike Eric, who built the monster 6502 out of transistor stuff, which him. And so there's passion to do things is a big deal. And so doing your own microprocessor or circuit in your home, hey, that's awesome. I love that. I should mention that there's one microprocessor that was designed by a sister and a brother. And it's the one that was used in the Apple IIgs. My sister designed the whole thing about a year, and I did the circuit design of the whole thing. So it was a brother-sister that designed the 65816. So, one person could do that, but the actual building of it, that's a different thing, because there's a lot of chemistry involved with that and a lot of other things to make it work. And the actual geometry of something you build in your home was probably bigger than what would be, commercially viable.
Okay, and thank you, Bill. And yeah, regarding this project, we know about this, but maybe not to you guys. So we just like tell a bit more. So there is guys in California who just like, you've seen this chip, it's pretty small, and then the crystal inside is just like, I don't know, like half an inch or smaller, like the size of the actual crystal inside the plastic case, and it's really small. And the guys had an idea that to enlarge it like 100 or more times, and created a kind of a PCB with all the components, transistors, that is the basics for all the chips. They recreated like in the real size, like also in plastic cases. And so this is really big processor, and they used a lot of these blinking LEDs. So this is it looks like we really like the very enlarged version, and you can actually see how these commands are executed. So what is stored inside, and you can also visit this website, and I like the tagline from this website. Where like people they ask questions. It was like, guys, I don't know, like, are you nuts? They say, yeah, absolutely. Yeah, so and it's really a fun project. But yeah, but also, so I got, so it's don't do chips at home, just try to design them and send to some factory. So this is the bottom line because involves a lot of chemistry and it's really helpful for this and don't do it. Okay, and by the way, about the like typically it was like some companies did the design of the chips, but now we see that like the trend that, for example, Apple. They didn't want to buy chips from somebody, and they right now just want and really design their own chips. What I think on this is it's just a kind of like global trend for the big companies. They need to secure this technology and have all this expertise inside. And in general, like it's how much resources you need to build your own like generations of modern chips inside your company.
Okay, to design the chips like Apple. By the way, I just read an article the other day that TSMC, I don't know if you know those names, but TSMC is Taiwan, microelectronics, whatever. TSMC, semiconductor companies, whatever. Anyhow, so but they're actually the leading company. Actually, they're not the leading. They're the leading pure play foundry company today, and they're doing things at 3 nanometer, and Intel's having problems. I think it's 7 nanometers or 5 nanometers. I just read that their next chip is actually going to be manufactured by TSMC at 3 nanometers, and they're beating Apple. So Apple and Intel are designing the most advanced processors, and TSMC is building. But the most advanced, which is interesting, is Samsung. Samsung is already in manufacturing commercial chips on their gate all around, GAA, gate all around chips, which means that they can shut off the leakage in the channel because they have the gate all the way around the transistor. And when I was designing them, or when we design them, you just have it on 2 sides. So gate all around is the latest, and I think it's at 3 nanometer. But anyhow, what do I think about it? Well, go back to Steve Jobs. He wanted to close up the Macintosh. The Apple II was all open. Like yours is really open, right? Your SmartyKit is really open, so you can do all kinds of things with it. But Steve Jobs said if you open up his Macintosh, you void the warranty. So this is another one of these things where if you go to the screen, you build the next generation system on a chip, most powerful microprocessor. So you're trying to get an advantage. Now, Apple went from almost out of business, bankrupt, almost bankrupt, and Steve Jobs got Bill Gates to invest $500 million into Apple to keep them going. Then they become the most valuable company in the world at $3 trillion. Wow. So in other words, when you have that much money, when you have that much influence in the world, I think you ought to be able to design your own chips. Now, how many people does it take? I'd say at least 500 engineers. That's a lot of engineers, and it's a lot of management. It's a lot of whatever you want to call it. But the way that Intel and probably this is what Apple's doing probably now, is you have maybe 2 or 3 teams. So every 2 years, if you want to turn out another processor, you're going to need, 2 or 3 teams, maybe 4 teams. So you might have 4 times 500 engineers. So there's a lot of people involved with that. Now, is that a good idea? I think it's a great idea. It's just that's not me.
Okay, so in general, like if you're getting bigger and like the core thing is like you can really find these engineers. I think the problem was also to find these guys and to hire them. Like you can solve this and you can have these teams like only working on the generations. And so for sure for the business at this point, I think it's good because they can do all this. But when you like, for example, because the general idea of like specialized companies, like they have like more resources in order to build the cutting edge technology, but when it blows up, your engineers, they don't really see like all the trends. I don't know, and they can't really communicate with the guys from Samsung, I don't know, from Intel, and exchange their opinions. And maybe this would be a hurdle for them, and in order to move on like 5 years perspective. What do you think about this?
I'm not sure I got what you're asking.
Yeah. So in general, as I got your point is that it's good for Apple to have its own team, and but in like in 5 or 10 years time frame, if these guys from Apple would just not, they are not part of like independent contractor who can like see the full market and work in this field, maybe their like expertise will be like limited, because they're like just like gold working just in company that is not really specialized in CPUs in general. It's much more about in general, there are a lot of other priorities. And hopefully like in 5 or 10 years, these guys would be like not on the front line of the technology. What do you think? That could be risky for them, or just like, or it's not?
Okay, yeah, I got your trend of thought there. Actually, when you look at working at a company like Apple, you're at the forefront. You're really at the forefront, because you got the market. And so, but when you're on a team of, let's say, 500 engineers, you're kind of a number. I'm saying individually, you can do your part. So if you're going to build something with 5 billion transistors on it, you're probably assigned a few million. but just divided, you know, a billion divided by 500. So how many transistors does one engineer actually work on? So there's some of that. So you get isolated. You're going to be isolated. That's why I like small chips, small CPUs. But there's another thing going on right now that Intel, just as an example, they were a licensee of ARM, and then they spun off that ARM group in a company I think called Marvell. So what happens then is that Intel internally had a problem by managing ARM processors and evolving those with x86 processors. And you go, okay, so that's kind of splitting the loyalty between 2 different architectures. So, but now there's something else that popped up out of Berkeley. It's called RISC-V. RISC-V is the new ARM. But the difference between ARM and RISC-V is that RISC-V is totally open hardware and software. So it's a whole new ballgame. So that's where I'd say, I don't think, well, I don't know what Apple's going to do, but I have a feeling they're going to have to switch at some point to RISC-V. Now, another major competitor of the United States is called China. China is focusing on RISC-V. So China wants to do it their own way, but with the open platform that came out of Berkeley. So it's a very good processor system. In fact, they went to the VCM, a Vintage Computer Festival that we had at the Computer History Museum, and a couple of guys that were with the RISC-V developers were in the audience. And after the question and answer, they wanted me to respond to, well, what do you think of the RISC-V this last year? I said, I think it's a revolution equal to the 6502. And they go, so then they contacted me afterwards. David Patterson was one of them. David Patterson was one of the designers of RISC-V. He and John Hennessy, who was the president of Stanford, the 2 of them are the editors-in-chief of the leading computer architecture book. It's probably in its 5th generation, 5th edition. So anyhow, so what happens about earlier this year, Intel announced they're going to spend $1 billion on RISC-V, which is fascinating. Don't you think that's fascinating? So that tells you something about, are you going to be locked into an organization? Well, I think something like RISC-V will mean that if you're working on there, then you can go other places if you're experienced there. So that's what I think is part of this. But going back to what you're saying is, I like the small company. I like the startup role here. New ideas. And that's what I'm hoping these classes on how to build these systems on chips. Think about it. When I started my company in 1978, actually in 1980, I designed my own. We have our own design rules. There's a lot of details about that. But that was for designing at 3,000 nanometers. I can take the design that's in here because it's hardware described in software. I can take that same design, run it on this thin film, where I can run it at 3 nanometers. So now the 6502 on 3 nanometers, if Intel and ARM can get it to run a couple of gigahertz, I think the fastest they can do at Intel is 5 gigahertz. I haven't seen anything more faster than 5 gigahertz. But I just got an email from University of Notre Dame about doing 10 gigahertz. And so, but what do you do with the 10 gigahertz 6502? I mean, I have a hard time figuring out what you do with 100 megahertz.
Thank you, Bill. And also the question is about this concept of embedded intelligence that you stated, because it's really interesting, and just like, please tell us more about this.
Okay, so why do you design a microprocessor in the first place? Notice microprocessor. Now, ENIAC would be considered a room processor, right? But why do you do a microprocessor? It's to embed intelligence in the thing. So I think of artificial intelligence as really embedded intelligence technology. Now, when you think of working with the cloud services, and you have something like this with data, right? So what we're talking about here is this is a distributed embedded intelligence technology, but it's embedded in the thing. This has got a lot of stuff in it, and it's been evolved over the last, 20, 25 years. So it's really a powerful system. So when you think of embedded intelligence in things, then you stop and say, one day, maybe about 15 years ago, wait a second. We humans want to figure out how nature works, and then we create things like nature. Then I started thinking, hey, wait a minute. Everything has to have an embedded intelligence to be the thing it is. It's really a simple idea if you think about it. And why are we in school, or why do we take, why do we want to learn about this? It's to enhance our individual embedded intelligence. So if you take a community like a town or a city or a state or a country, then you'd say there's an embedded intelligence distributed in that particular community. And it's a community you want to be part of, hopefully. And so at that point, you're all working, let's say, more or less as one, as an embedded intelligence that's distributed. So when you think of that, right, when you start thinking differently and see one of the things that I think has been a problem for a long time for humanity is that if you're feeding them bogus information or mythological information, and the other party, the other person doesn't know it's a myth, then you're believing in or trying to apply something that isn't proven. Well, as an engineer, all these things work. And that's because I'm using real science. And so that's the way I look at this. And so the idea of embedded intelligence and the theory of embedded intelligence said Everything to be the thing it is had to self-assemble. You self-assemble yourself from information from your mother and your father. And when you contributed your animating energy, that means that you wanted to do this. You figured it out. You want to do this. Now, you probably don't remember it when you were just a cell from your mother and father, but factually, that's correct. So therefore, if you think that way, then what's happening right now in the world is we're starting to understand quantum. You've heard of quantum processing? Okay. Well, what's interesting is everything you see with your eyes or your five senses is built out of quantum. So nature is quantum, or quanta, which is the plural of quantum. So when you look at some of these things in that way, you're looking different at it. And so when you think about this quantum computing, now you know there's a big effort by IBM, Google. I didn't hear Apple, but Apple's got to get in there. That's too good of a plan. And so you have, I don't know if Facebook's in it, but you know, Google and Microsoft, IBM, and there's got to be others. There's got to be others. And so they're trying to figure out quantum. And the reason why they're trying to figure out quantum is because if you split a photon or you split an electron, then you can send one half of it in that direction and the other half in this direction. And because you split it, you can observe what's going on here, and that will cause it to objectively reduce or become a particle. Like for instance, with electrons, if you split an electron, one half of it will have a spin up. And as soon as you know that, the other one instantaneously becomes down. And so now you can use this to communicate. And that's where they're trying to do these encryptions so that we can do message communications and encrypt information. Now there's bad actors and good actors. So if you think about the quantum form of things, it's a probability, and a probability it would be up or down. So if you're looking at electron, but at the same time, it means it's a probability of bad actors and good actors. So I like thinking that the objective reduction of the wave function is probabilistic. That means 50% of us are going to be bad actors, and 50% of us are going to be good actors. Just look at the voting here in the United States, and you'll see, oh, 50% are voting for one side and 50% for the other side. Well, that's the probabilistic of quantum mechanics. So the idea of entanglement is a huge deal. And so when you think of what's the 2.2 pounds or whatever it is between our ears, is the most massive quantum computer in processor in the universe. And so one of the things that I gave a workshop on this in April, but one of the things that you can think about here is that if we are so powerful, then you know we're not using just but a tiny fraction of our capability. But when we focus our passion on building SmartyKit, then we're using it in a good way, right? So to me, I think we can look at this as a positive way. And one of the things that I wanted to introduce you to, I was just introduced to it earlier this year by actually the Associate Dean of the College of Global Futures at Arizona State University. And he gave a talk on, and within his talk was a concept about a bounded infinity. You know, bounded infinity, I haven't heard of that one. And so he said, yeah, like odd numbers is bounded infinity. Oh yeah, so there's no even numbers, just odd numbers. But if you thought of the biggest number, one more, right? And so then he also said that even numbers is about it. So when I got on a Zoom call with him, I said, so Andrew, thank you for the bounded infinity idea. Do you think that a human is a human bounded infinity? And he did one of these things on the Zoom call. No, but that's a good idea. And so that's what I wanted to tell you. You are individually a bounded infinity. And it's what do you want to do with your bounded infinity?
Thank you, Bill. And now I think it's a question time. If you just like want to know more about this table that are in choose making or anything about the computer store electronics, just please go ahead. Like, yeah, do you have any question, guys? So I think Dave or Dave combination.
Yeah. Well, what he's doing for was really amazing. So my question is, you mentioned that well, TSMC is about 3 nanometers of process node, and I heard that there is 1 nanometer process plans in next couple of years. What is when will we face the situation when well, like physics limitations stop us from like further progressing in traditional chip development? Or it can be like, oh, will it be replaced by quantum computers? What is it?
Okay, so when are we going to reach the end of the line for Moore's law?
Yeah.
That's what people talk about.
Yes.
Well, I think we're there. I think it's just that for marketing reasons and for selling chips, nobody wants to know we're at the end of the line. But quantum is another thing that, for instance, when I do this, okay, this is quantum. I'm quantum. You're quantum. This is classic. This is classic means quantum. Okay, so we're already there. The idea of building quantum computers that have to be, they're built in the coldest place in the universe. That means that they can't find a place colder than minus 273 degrees Kelvin or whatever the number is. So the quantum is an interesting thing. Now, I'm talking with some professors, one at University of Tennessee, one at Oxford, that are talking about, and they've written papers on it for like a dozen years or so. And that is quantum DNA, quantum RNA, quantum protein. And so also a friend of mine, his name is Stuart Hameroff, who works with Roger Penrose, who got the Nobel Prize in Physics in 2020. They're talking about quantum, they're called microtubules, but they're trying to figure out how our brains work, how our cells work. So you have to go to quantum to figure it out. And some of the famous people like Schrödinger, Heisenberg, Einstein, von Neumann, and Princeton. Some of these people were working on about 100 years ago, working on quantum stuff. But when you think quantum right now, you're thinking different. And a part of that is quantum mechanics, is this entanglement part of it. And so to me, when I talk about embedded intelligence, I already know it's there. I just don't know how it works. I'm not trying to figure that out. I'm trying to apply it. What I'm saying to answer your question, I think there's going to be quantum processing, quantum computing, and there's a Hartmut Neven, who's another person that I know now. He's the head of AI for Google Quantum. And he also sponsors a quantum neuroscience conference each year in Santa Barbara. I just happened to meet him and get to know him and talk with him about quantum this. He did something special. When we were on Zoom, he acted out with his body a wave function that objectively reduces it. I thought that was special. But it was his embedded intelligence that did that, right? So therefore, I'm just saying, I know it's there. I know it's got to be there. And it's like, okay, so I'm not going to be the one to figure it out. I just know it's there. It's just, but I'm not going to do the science that will get you there. There might be professors that or researchers all over the world that want to figure this out. But coming back to your question, they're doing 3D now. In other words, we're stacking chips, and they're called chiplets, I think. And so you're stacking chips. So that's another way to get 3D and get more bandwidth to communicate between one chip and the other. So it's getting more complicated like that. But at the end of the day, I think you have to get the humanity, has to be down that path. And if we're the good guys, hopefully, I'm in a good guy room right now. We just have to stay ahead of the bad guys. But there's 50%, and that's the probability of 50% good guys, 50% bad guys. As long as we know that, we're not gonna eliminate the guys, and I certainly hope we don't eliminate the good guys. But coming back to you, I think, there's always gonna be advances, and it's gonna be like what I just said. I think they're gonna start stacking the chips. But as far as Moore's law, I think we're basically there. When they talk about 3 nanometers, if you actually look at what's going on, they have about 9 layers of metal. Diane and I, when we designed, we had 1 layer of metal first, then we did a second layer. But we've never needed 3 or 4 boxes, 79. But the idea there is that when you look at what they're doing, 3 nanometers doesn't necessarily mean the transistor or 3 nanometers. It's just a marketing game. So when they do 2 nanometers, it's just, okay, we got another number. But it might not be 2 nanometers for line widths and spacing, etc.